Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Today it's my pleasure to introduce Jens Teuber. He is leading the Database Information Systems Group at TU Dortmund University in Germany. His research interests include, are really data processing on modern hardware platforms. This includes FPGAs, multi-core platforms, and hardware-accelerated networks. So with that, I'll keep the introduction short. Jens?
Yeah, thanks a lot, and thanks for all coming. Of course, feel free to interrupt me. I've given this talk a little bit of a catchy title, sort versus hash. That's one of the long-standing debates in the database community. It's like a pendulum swinging back and forth. What is to be preferred as an approach? And I'm going to look at this discussion in a main memory context. So I didn't exactly know how deep the database knowledge is in that audience. So basically, for all of the core database operations, be it aggregation, grouping, duplicate elimination, or joins, they basically all boil down to a very similar implementation, which can be based on sorting or hashing. In this talk, I'm going to focus on joins. So for the most part of the talk, I'll talk about joins. So we want to implement joins in main memory as efficiently as possible. And again, there's basically two approaches. One of them is to use hashing. So a hash join, I just, as a recap, try to visualize it. What you do is you have two input tables. And what you do is you scan one of the two input tables. While scanning the input table, you populate a hash table with all the tuples from R. And then in the second phase of the algorithm, you scan the other relation and for each tuple probe into that hash table. Hash join is popular because it has nice complexity properties. I wrote here a little bit fuzzily O of n, so it's linear in the sum of the sizes of the two input tables, and it's very nice to parallelize. We'll see that in a bit. Alternatively, and that's what I think databases that run off disks preferred today is the so-called sort merge join. So what you do is you have your two input tables. They are in some order. So as a first step of the algorithm, you sort both input tables. And once they're sorted, joining all of a sudden becomes trivial by just merging the two. So that's the so-called sort merge join. It's used a lot, I think, when you deal with external memory, because databases have techniques to deal with, to sort arbitrary amounts of data quite efficiently. Strictly speaking, its complexity properties are not quite as nice, but we'll see actually in the end they both boil down to be very similar. Now I said I'm going to look at both sides in a main memory context. So the question is, which of the two strategies do you want to prefer in a main memory context? Classically, hash join has always been the preferred choice because, well, if you take random access memory in its literal meaning, then this random access pattern of the hash doesn't hurt you when you run stuff from main memory. And then you prefer the simplicity and the nice complexity properties. But the question is, how does this look like on modern hardware? And that has, like in the past years, led to quite a bit of discussion in the community, which of the two strategies should be preferred. I think one of the quite well-known papers here is one that a team with people from Intel and from Oracle did, was they did a study where they wanted to compare the two, and they tried to make predictions of what's going to happen in the years to come. And what those guys found out was that the hash join in their setup was the method of choice. It was about 2 times faster than sorting. But they predicted that as hardware emerges or evolves, it's quite likely that very soon sort merge is going to overtake hashing in performance, and that is because of the increasing SIMD width for the vector instruction capabilities of modern CPUs. Those tend to be a very good fit for sorting, but not so much for hashing. That favors sort merge join. And their projections from about 4 years ago were that if you have an architecture with 256-bit SIMD registers, then both should be about the same speed. And after that, as SIMD vector lengths continue to increase, sort merge is going to be faster. Now, more recently, a group from Wisconsin, they looked at hash joins only, and they sort of did conclusions only within the hash join world. We're going to see what exactly this statement here means. What they basically said is that a relatively naive implementation of hash join is superior over implementations that are highly specialized to modern hardware, highly optimized to modern hardware. I listed that also because even more recently, there was another paper that did compare sort merge and hashing. That's a group from TU Munich. They took these results here, did a transitive conclusion. So they found that their sort merge join algorithm is faster than this hash join implementation, and by transitivity, this is also faster than this one, which means sort merge join is the method of choice. That's kind of what they say. Yeah?
So these results assume that you have similar sized relations on both sides, or? Because you can make hash join look arbitrarily better by if you have a tiny build side, right?
We're going to see that indeed a little bit, right? And so in fact, that kind of brings us to what I want to do in this talk. I want to, of course, the comparisons on that previous slide, they were really apple to oranges comparisons, right? In particular, these transitive conclusions, right? You choose different work, you prove something on one workload, and then the transitive conclusion on another workload. So from that, you can conclude anything. So
the n log n, of course, will eventually, if the n is large enough, dominate any constant factor, which you might get from the linear one. So it depends on how big the relations are also overall, what you're going to get.
Sorry,
Sort merge is n log n.
Right?
That will eventually dominate any algorithm n in terms of its total cost will be larger.
Yes, but it turns out that efficient hash join implementations typically also we'll see that you do multipass hash joins, and then you end up with a log n factor again. So it's not really clear whether that complexity argument really makes sense. Okay. So yeah, what I'm going to do is I'll try to do apples to apples comparisons, and I'll sketch a little bit like implementation details that we found out to matter, and we try to, or I try to, in the end, make a little bit conclusions about where are we in terms of the sort versus hash discussion. So the agenda for today is I'll first look at hash joins in more detail, then at sort merge joins, and then I'll compare the two. Okay. So again, hash join is nice because it's so nice to parallelize. So what we're going to look at is of course, we look at modern hardware, so that includes multi-core parallelism, of course. This is just a slide to show that hash join is basically trivial to parallelize. You just chunk up both input relations into partitions that you assign to individual cores, and then you can do the hash table build and the probe in parallel, of course, still one after the other, but then you can use all your cores to do a joint build and a joint probe. This, in principle, works very well. That's because you do need a locking mechanism here, because in the build phase, the hash table is accessed concurrently. But you benefit here from the cardinalities are easily in the millions, right? And then the chances of getting a collision on that hash table is basically negligible. So this parallelizes very well. You won't see any lock contention in practice, just because there's so many hash tables, hash table buckets in practice. So this is like the basic hash join implementation that we're going to look at first. And this is what this group from Wisconsin claims to be the preferred one because it's fast and because it's simple. Now, if we first look at, so what we did was we took their implementation, analyzed it carefully, and tried to see whether the comparisons that they make are actually valid, whether they make sense, or whether they're doing apples and oranges comparisons. And for that, what we first did was we tried to see whether there's any kind of situations where we can improve their code. And I have one example here just to show you that you have to be very careful to implement such an algorithm. Otherwise, you're going to suffer quite significantly from effects in modern hardware. And one of these examples is, so what I'm showing here is the hash table implementation that the people from Wisconsin used. So in order to implement that hash table, you need some locking mechanism. So you have they implemented that as a separate latch array. And then the hash table consists of a hash directory that points into individual buckets that are allocated from a heap. Now, when you do any operation on that hash table, what it means in the end is you need to access 3 different locations in memory. You need to first get a latch, then you need to follow the pointer, and then read out your data, which amounts to 3 memory accesses per tuple. And of course, you can also do that with just a single memory access per tuple by simply collapsing that into a single data structure. And why that is important, you see on this slide here. So when you start analyzing the performance of that implementation on modern hardware, what you'll see is that so the amount of work that you have to do per input tuple is actually extremely small. So looking at the hash table build phase here, what you need to spend is per tuple about 34 assembly instructions. And now it makes a real difference whether during those 34 assembly instructions you see 1 or 3 cache misses. In practice, we saw something around 1.5 cache misses. That was because, well, it depends on how you cache line align your data. You can also bring that down to 1 if you want to. And we saw TLB misses quite a lot.
So these numbers are for your modified
exactly, yeah. These are for this implement. So here you see 3 misses. Here you see 1.5. The 1.5 comes from, so if an aligned address starts here, right, then this is the first row, and the next one will come right after here, and it will span over 2 cache lines, and then you get two misses for just a single read. And then you can do a trade-off. We played around a little bit with that. You can, well, we wanted to keep the number of tuples per bucket consistent. Otherwise, you just you introduce another parameter, which you can vary around arbitrarily. You can blow up a little bit, so you spend more memory, which causes you more cache more cache occupation on one hand side. But with aligned access, you can reduce the amount of cache misses per tuple. But performance-wise, it didn't make a huge difference. Okay. So either way, what you end up with is you have in the order of 30 CPU cycles work to do, and that, well, and at the same time, you need to do, well, 1.5 memory accesses plus a bunch of TLB misses that you'll suffer. So here, you're easily talking about 200 cycles or so that you need, right? So in the end, you're going to be severely latency bound, right? All the cost you're measuring is those cache misses. And that's why in practice, or we think that such an implementation on modern hardware won't make sense. People have realized that earlier. One way to avoid these many cache misses is to choose a partitioned hash join instead. So the idea there is that before you build up your hash table, you break up your problem into sub-problems. So you use hash partitioning to break up your input relation in cache-sized chunks. You do that for both input tables, and then you basically need to only join corresponding partitions. And if those are small enough, then you can keep all the processing for one such pair of partitions inside the cache, and you won't see any cache misses anymore here. So once you do that, you can each of those joins basically runs out of caches, and you will see basically no cache misses anymore. Again, you have to be careful when you implement that. So what the Wisconsin guys did is they took this very literally. They partitioned, built all the hash tables, and then probed into all the hash tables. What this means is that you build up this hash table, you build up all those other hash tables, and eventually you've done with all your hash tables, and then you go back up here, and by the time you want to access that hash table, it's of course gone long since from your cache, right? If instead you interleave the build and probe phases, you can reach a situation where you build up that hash table, it sits in the cache, then you probe from that side, you use the data that's readily in the cache, and then you move on to the next partition. And again, you can save a lot of cache misses from that.
So this is a symmetric question. So you have both relations in memory?
Yes. I mean, throughout the I assume everything's in main memory. Yeah. I didn't say that explicitly enough. So what I'm assuming is I have everything in main memory. We also assume like a pretty much column-oriented storage model. So we assume very narrow tuples. So you saw that here. So we assume in that case, in that picture, we assume 16-byte tuples only. Eight.
But if one of the sites is really another join, then do you get do you get streaming there?
You get what?
You can one of the sides. You can have multiple joins going on, right?
Right.
You can have R join S join T.
Right.
The R join S feeding into the top join. You have to keep the result of that also in memory, right? Is what you're saying.
Well, but the join is blocking anyway. I mean, you anyway have to.
But what I'm saying is, it's not enough to have R and S in memory. Now you have R join S also in memory. To compute R join S join T.
Yeah, but you need to. I mean, either way, you need to keep the. Either way, when you build up the hash table over R join S, you need to keep that in memory anyway.
Yeah. But in the traditional, external approach,
yeah.
You would only keep one of the sides in memory.
Okay. Yeah. Okay.
If you have the space, sure.
Okay. Yeah. I mean, this is really assuming memory is cheap. Just have everything in memory. Yeah. Which I think is increasingly reasonable. I mean, you guys are working on in-memory processing as well, right? So yeah. Okay. Once we do that, we indeed basically avoided almost all cache misses. You still have some. I mean, at some point you still have to bring stuff in cache. So you do see a bunch of cache misses, but not many. And at the same time, the nice thing about this partition hash join is that after partitioning, you end up with a lot of independent work. So no need for a shared hash table anymore. You can just do the R1 join S1, R2 join S2. You just do those on separate cores, and there's no need to synchronize through locks anymore.
Can you explain a little bit more why it's independent? Do you sort them or something, or like how are the partitions created?
Well, you can only find matches between here and here, but not between here and here. Okay?
Why
Because you hash partitioned here.
Oh, like a regular partition.
Yeah,
okay.
so you use your key value as a partitioning function. All tuples with the same key will go into the same partition, and you use the same partitioning key on both sides. Okay, so you will only find matches between, how can I say that, neighboring partitions here. And then you can run this join on one core and this join on another core, and they won't interfere at all with each other. No need to protect with locks or anything. And that makes your code even simpler. So we end up with 15 to 21 instructions per tuple for build and probe phases. Almost no cache misses anymore. So this join, we've reduced quite a bit of the cost. Yeah.
So can you go back to the previous slide? I just had one clarification question. I'm still not very. I don't understand exactly what's the difference between the picture here and the picture in the previous slide. Is it that each of your rows is now big enough so that I don't need to follow next pointers to enter values into a bucket? Is that the main difference, or am I lost?
Well, because you partitioned this stuff here, these hash tables are now hash tables over just a fraction of the input. In practice, you don't do just 4 partitions. You create thousands of partitions. Okay.
How is each partition implemented? If I implement the partition as a linked list again, I would be the same data structure, right?
Well, this is just a part of your table. It's just
R4 plus S4 fits in cache, right?
Huh?
R4 plus S4 fits in cache.
Yes, it's actually enough. It's enough to have the hash table in cache. So R4 has to fit in the cache, assuming that the hash table is approximately the same size as a table, right? The hash table has to fit into the cache. That's enough, right? So you break up this input relation into chunks that are cache-sized. Suppose you have, 400 megabytes here. You have a 4 megabyte cache. You create 100 partitions. And then for each of the partitions, the hash table will fit in the cache. And then you can run the hash join from the cache.
You don't get any misses, TLB misses, anywhere.
So in the next slide, you said there's 0.01.
It's basically it's of course you always do get some, right? There's always some compulsory misses, right? But these are
How do you avoid misses during probe?
during probe, everything's in the cache.
But the assumption that
After you hash, basically you have pointers which have at random addresses, right? After you hash, it's not necessarily that these pointers are sequential.
Yeah, but they're all, this is small. This fits into the cache. And once stuff is in the cache, then that's what the cache is for, right? Once you keep on both sides, once you keep that contained in the cache, then you won't suffer any cache misses anymore. And even the TLB also is enough to cover the entire hash table if the hash table is small enough. Yeah.
I think it's a follow-up that might address some of this. But the partitioning itself should spray your thing all
Exactly. That's
Not counting it in the next slide, right?
That's what's coming next. Yeah. Yeah. That's what's coming next. Yeah. So what I did not yet tell you is that partitioning itself introduces a new cost, and that's where the TLB indeed comes in. So if you do partitioning, then it depends on the number of partitions that you want to create concurrently. Partitions are roughly cache-sized, so it's safe to assume that one partition is larger than a memory page. A memory page is just 4 kilobytes. So in the end, each partition will reside on a separate memory page. So you need a TLB entry. If you want to do partitioning, you need one TLB entry for each of the partitions in order to write into those partitions. And we have some experiments for that. So when you start, so when you do partitioning, so these are assuming just a single partitioning thread. Now, now you vary the number of partitions that you want to create. So this is the logarithm of the number of partitions. So you create 2 to the power of 4 up to 2 to the power of 16 partitions. And what you can see here is that for a small number of partitions, partitioning can be done very, very efficiently, about 100 million tuples per second. That's because partitioning, it's conceptually, it's very, very little work. You just compute a hash value over the key that tells you where to put the tuple, and then write it there, and you're done. It's not much work. But once you
cache miss properties too, of course.
Yeah, the cache misses are not really problematic because you're talking about here, let's say 2 to the power of 14 addresses where you're concurrently writing to. So you need about 2 to the power of 14 cache lines, right? And that's not much data. That's it's a few kilobytes. So because you write into each partition sequentially, right? It's like having whatever. If you would do that in a file system.
Why are you assuming that you write into each
Partition sequentially.
No, I can see how you could write into the partition sequentially, but the actual process of partitioning is not sequential. That is to say, as you process a tuple.
Yeah, but for each partition, you only need to keep like the next position in memory, and those next partitions, those aren't many. That's not much data in total. So you can get that in a cache, right? For each partition, the slot for the next tuple to insert, that's just 2 to the power of 14, say, slots. That's a few kilobytes of space, right? You can, like in the classical database, you can create you can create partitions over terabytes of data with just a very small buffer pool, because all you need to keep in the buffer pool is just the next page to write out for that partition, but you don't need to keep the full partition or something in the cache. Does that make sense? No? You're skeptical still.
Well, the total number of misses is the total size of however many elements you have divided by the number of entries that you can fit on a single cache line, effectively.
Yeah. Yeah. But yeah. But you know, the how can I say that? Yeah, it's all. You're writing into each partition sequentially, so very likely you have for each of those partitions the area around your current writing position. You have that in your cache, so you don't need to. You don't. And then writing there gets quite efficient because you just need to write into the cache, and then if that cache line is full, it's being written out to memory, but you don't even have to wait for that. You can still continue. It's write only.
But at best, it's the total number of entries divided by how many you can fit on a single cache. Because you miss and then
right.
fill. Now it's full.
Yeah.
Okay, now I got to chuck it out.
Right.
So,
Right. But that's different, like when you during a hash table build or probe, where you randomly put individual tuples in there. Then typically you have to bring in the cache line, do the update, and write out the cache line again, because you don't write those. You don't have this sequential pattern as you have it in partitioning. I don't know if I'm making sense. Okay. Now the problem is, of course, we want to create many partitions because we want to have those partitions small so they fit into the cache. The smaller the better, so we can bring them in L2 or something cache. In practice, in our experiments, what we would like to be for the data sets we used, you would like to be around here, so 2 to the power of 14 partitions. For the workload configurations that we had, this was a good choice. But you know, in this picture, it doesn't matter much whether, you know. Now, what can we do about this? And the classic way of doing that is multipass partitioning, or also called radix partitioning. It's basically an idea that's been done also in disk-based systems. You're limited by the number of partitions that you can write concurrently. So if you can write at most, say, 100 partitions concurrently, you can just do multiple passes and refine your partitions again and again. And this way, you never exceed your maximum number of partitions per partitioning pass, and still end up with as many partitions as you want in the end. And that's where the log n factor gets into hash join, right? Because now you have to start partitioning in multiple passes, and the number of passes is logarithmic in the amount of data that you have. Okay?
In some respects, it's all partitioning. The last step included.
Yes, it's true. It's true. Yeah, it's basically the same operation, hash table building, and it's true. Absolutely.
You can terminate at any time you figure your bucket is small enough.
It's true. Yes. It's true. Yeah, and if you do that, it turns out the cost of an additional pass, it's additional CPU work that you do, but it saves you all those TLB misses. And as you can see here, for the area where we're interested in, it gives a significant advantage in terms of the partitioning cost, right? You can do better even. The trick here is that, so this is how you implement partitioning naively. You take a key, hash it, and then just write it where it belongs to. Okay? What you can do alternatively, and then this is always a write, right? And for that, you need a TLB entry for writing that element out to memory. What you can do instead is like create like a little buffer in between. Oh, I've written this as an algorithm here. So you would hash your key, not write it out directly to memory, But first, fill up an in-cache buffer. And only when that in-cache buffer is filled up, then you flush out the entire buffer slot out to your partition. So for each partition, you have a little buffer. You fill up that buffer, and only when the buffer is full, you flush it out to the partition. What this means is that if you can have something like 8 tuples in each buffer slot, you get a memory operation, or an operation that goes all the way to memory that needs a TLB entry. You need that only every 8th tuple, so you can push down the number of TLB misses. And once you have sufficiently few TLB misses, then they won't cause any harm anymore, because then all the out-of-order mechanisms in your CPU will be able to hide the latency that you get from those TLB misses. Right? You can just keep processing while the hardware just does the TLB miss for you. In practice, you choose your buffers to match the cache line size, because then you can do those transfers particularly efficiently.
The effectiveness of this buffering mechanism is only as good as your hashing function, right? Because if your hashing function sprays the loads all over, then you might wait too long and waste lots of memory.
Yes.
So, was there any correlation in any case between your actual data and the hashing function? Or,
well, you know, we don't have, as an academic, we don't have real-world data, so we were dependent on synthetic data anyway, right? Once you operate on synthetic data, then you can use anything for a hash function, because you don't have that nasty type of correlation in your data. So we kind of cannot really.
I mean, it depends on whether you're dealing with distinct values or not. Yeah.
So what we
If you're
did
not
do.
dealing with distinct values, then you have all sorts of distributions.
Yeah, what we did do, but I claim that's kind of independent of the hash function, right? If you have duplicate values in your data, yes, I didn't bring experiments with me, but we did measurements with skewed data. But still, then you don't have funny correlations between the data that would affect the hash table. So how can I say that?
Say you have sequential keys and your hash is like CRC32 or something. Each row will go a totally different place. So this buffer will be usable in some sense. So.
Oh, because the radix that you use for the hash depends on how many you can fit.
So I'm trying to understand, was there any knowledge of the incoming data to make the hashing function friendly enough to leverage the buffer, or?
Yeah, because the moment you generate synthetic data, I claim they're always, every hash function is friendly enough. Okay. Unless you build very funny, very, very artificial distributions where, so we used zip distributed data, but we permuted our alphabet beforehand. Otherwise, you do get very strange effects, but they don't reflect reality either. Okay. Yeah.
But again, if you have non-distinct keys and they're distributed in some way so that you get 50% of the keys are all the same, or 25% of the keys are all the same, you can have very bad skew.
Yes. We did do measurements. I didn't bring them with me, but I can say a few words once we. So actually, we'll soon see a bunch of experiments, right? So once you do this, it turns out that with a single pass, you can actually over quite an interesting range of partitioning fanouts. You can do with a single pass even better than with radix partitioning, which is, I think, well, up until now has been always considered sort of the strategy of choice. So putting this together, what I'm doing, what I did here is I show some measurements that we did comparing this what the Wisconsin people called no partitioning join, that is a hardware oblivious join, not considering any caching effects or anything, versus this radix join, which does the partitioning and all that stuff. What you see is that partitioning indeed gets responsible for a large share of the cost, whereas once you partitioned, doing the actual join gets negligible cost. So this is the number of CPU cycles per output tuple of your join. Contrast to that, because of the many cache misses, of course, that you lose a lot of time in the build and probe phases of the no partitioning algorithm. This is a benchmark configuration that we took from the Wisconsin paper. To give you a feeling, so on our Nihilum machine that we use, it's like I think it has four cores. You get in the order of 100 million tuples per second in join throughput.
Do you have another chart which shows the LLC cache? I mean, the row-level cache size for each. I was wondering if there a correlation between cache size and JIT.
I don't remember. No.
You have a really big LLC.
Yeah.
Can't really remember the numbers between the Halo and Sandy Bridge, so I'm just wondering if there's a correlation between cache size, this algorithm, and these results.
Well, this difference here comes from the Sandy Bridge having much more cores. So this is a parallel implementation, and then you basically this is a measure of wall clock time, kind of. Yeah? So you have more cores, you need less cycles per tuple.
My assumption was the number of cores used was fixed. It was just measured different chipsets. So this was so basically we used in all those machines we used one socket, but used that, I mean, fully. There was this question earlier about the impact of first of all. So to show you that we work carefully. So we really tried hard to make both implementations as fast as we could. We think we can show that by showing that our implementation is roughly a factor of 3 faster for both cases, approximately, as compared to that existing paper. Now, what you see here is that, the Wisconsin guys, based on a picture similar to that, actually they had just those two sites. They argued that the hardware oblivious implementation is still preferable over a hardware optimized implementation, because depending on the platform, chances are higher to get to pay a penalty here as compared to the little benefit you get here. Now, once you go to a different workload, so this is the workload that has earlier been used in the literature, all of a sudden the game changes quite a bit. So these are two equal-sized partition relations, and there the hardware-conscious implementation clearly has an edge over the hardware-oblivious implementation. The hardware-conscious implementation also scales very, very nicely. So this is a Sandy Bridge machine with 8 cores on one socket. And if you start scaling that up on a 4-socket machine, you can reach cache throughput, join throughputs of about 600 million tuples per second. There was the question previously about skewed input data. It turns out that the hardware optimized version, this radix partitioning, turns out to be much more robust towards skewed distribution. So you get about equal performance over quite a wide range of skew values. The hardware oblivious implementation is quite skew sensitive. There you typically get an advantage from skew because your caches get more effective because you hit the same cache line more often. Yeah. Okay. So a conclusion from that is that hardware oblivious algorithms, if you choose the right benchmark, they do look good. But so we have an ICD paper on that. There's some more experiments in there, and those all indicate that with hardware conscious algorithm, you can typically do much better. And interestingly, we found that these hardware conscious implementations are extremely robust also to the parameters that you choose. So there's a few parameters in there like cache sizes and number of partitions and all that stuff. Yeah? Of course, getting those parameters right might affect the performance that you see. But it turns out it's actually, the algorithms are quite robust toward that. So a slight missetting of those parameters won't kill your performance at all. It doesn't make much of a difference. Yeah? Okay. Let's then have a look at sort merge joins. So sort merge joins, essentially there, all the cost boils down to sorting. Once the data is sorted, doing the join becomes almost trivial. Sort merge, and then the sorting part, you typically implement as merge sort. Sorry for the name confusion. That is, you first create some pre-sorted input runs, and then you merge them like recursively until you end up with a sorted with sorted data. In practice on modern hardware, I try to visualize how this looks like in practice. In practice, what you do is if you have a large system that's going to have a NUMA memory architecture. So here on the graph, I assume you have 4 NUMA regions. What you then, or one way of doing the sorting then, is to perform first. So you assume the input data is somehow distributed over all your NUMA regions. Then you typically do first a local sorting within each NUMA region to avoid memory traffic across the NUMA regions. Then, if you want to obtain a globally sorted result, which I'm assuming here, then what you need to do is you need to merge across those NUMA regions, as shown here. So you do the two-way merge here, and another two-way merge. Two two-way merges here, and then another two-way merge here, until you end up with a sorted result.
You're paying the NUMA penalty in the second step anyway, right?
Pardon?
The penalty of local versus remote NUMA, it's being paid in the second step anyways.
Yes. But you want to avoid moving data back and forth or something, right? So here, at least clearly, if that is the result that you want to have, there's no way around getting this data over here. Yeah. So you need to cross that NUMA boundary somehow, if that is what you want as a result.
So you don't have to get everything completely sorted, right? You can have.
Yeah, we'll get to that. Yeah, that's true. Yeah. Okay. Now, I was already mentioning here the bandwidth that you need to do the merging, right? In fact, the merging is a pretty critical part in that sort operations. So for both parts, for run generation and for merging, what you can do is you can implement them quite efficiently using SIMD acceleration based on sorting networks. which is where the this Intel work said in the future this run generation and merging is going to become even more efficient if you have wider SIMD registers. Just a comment here, like in hash join, partitioning was similar to hash table buildup. Here you have a similar thing that merging for merge sort is a very similar operation to the join afterward. So there is a difference in the sense that it's tricky for that part to use SIMD because your tuples look differently, and that makes it tricky to use SIMD. But other than that, it's a very similar task. So what we're now interested in is the merging part mostly. Here I have some numbers for both parts, for run generation and for merging in the merge sort sense. If you implement this well using SIMD operations, assuming you create runs with 4 items each, initial runs, you can do this with 26 assembly instructions. And for each of these assembly instructions, so with 26 assembly instructions, you can sort 4 sets of data. And then assuming 4-byte keys and 4-byte values, you end up with reading in 64 bytes and writing out 64 bytes. So in total, there is a ratio of 26 assembly instructions to 128 bytes moved between memory. Right? Similarly for the merge pass, so you can do merging also with SIMD. There, for every 4 tuples, you spend 16 SIMD operations and 4 load store instructions. What that means in the end is that you do a lot of memory I/O compared to the very few assembly instructions that you're doing for the sorting in between. So in practice, sort merge join gets severely bandwidth bound. So you're going to be bound by all this memory traffic. And I'll get to there was this question about global and local sorting. We'll see that in a bit, where this problem gets even worse when you do it wrong. Yeah.
Did you evaluate using hash for sorting, like creating a hash table,
Like arrange partitioning?
and creating the partitioning, and then you have the sortedness on the hash values bucket?
Well, that's radix sort effectively, right? We didn't try radix sort. There is, I haven't really verified that yet. You can do quite well with radix sort as well. I don't have a like apples to apples comparison between the two. Group at Columbia is currently proposing that.
The build phase would be the same as creating the hash tables as we did in our previous hash join, and then instead of lookup and probe, we can just use the sort merge.
Aha. You mean okay? Yeah. No. We didn't try that. We didn't try that. Yeah. So that would be a combination of hash join and sort merge join. Yeah. No, we didn't try that. That's interesting. Yeah. It's a good idea. Yeah. Okay. So we end up with both phases actually being severely latency bound. Now, what can we do about that? Now, things are still easy for the for the run generation part. So I said you need to write in and out these 64-byte chunks. In practice, that's not really a problem, because what you can do is you can you have this merge tree, and you take entire subtrees from the bottom, do them in one go, and then you have no real memory traffic. So you can do chunks of up to the size of your cache. You can sort them really in cache, and then memory bandwidth is not an issue as long as you're in cache. But for continuous merging, when you want to have your entire thing sorted, you don't get around you don't get around doing something about the high bandwidth need of merging. Now, one thing you can do is you, rather than just doing two-way merging, this is what makes your bandwidth demand so high, because you need to repeatedly do the merge. So you repeatedly need to basically reread the same data. But at the same time, two-way merging is highly CPU efficient, because you can optimize it so well with SIMD and so on. So it turns out the bandwidth cost is so high that it makes sense to give up a little bit of the CPU efficiency by doing what we call a multi-way merging thing. So what we did was we do a merging over, an n-way merging operation, which internally is broken down into a number of two-way merges, because the two-way merges, that's exactly that thing that you can do efficiently with SIMD, right? And now a single thread basically walks over all these pairs, all these merging pairs, merges a little bit here, merges a little bit there, as long as there's data there, right? It's like FIFOs in between, little buffers, and then you try this thread walks over this merging tree and tries to produce output, right? And the idea is to keep all these intermediate merging results, like streams, keep them within your last level cache, and have that thread again walk over all these merges. Yeah.
Are we trying to merge all the sorted data we have to create a bigger run?
Yes.
Do we really need to do that?
Yes. So I think 2 slides on or so. So I think that kind of clarifies the question.
Can you explain a little bit how this algorithm works? Because if I see that who's going to go for NUMA node 0, give me a buffer, NUMA node 1, give me a buffer, which is bigger over this one? 2 and 3, same thing, right? So this transition from one NUMA node to the other by the same thread, you're paying lots of costs for remote memory lookup, which is, effectively almost be as bad as the latency.
Okay. First of all, again, as I said previously, you cannot fully avoid crossing the NUMA boundaries. So this thread sits on one NUMA region, right? But at some point, you have to merge in data from the remote NUMA regions. And by the way, this doesn't necessarily have to come from separate NUMA regions. I just wrote it here. The point here is that you merge in from multiple sources. The thing here is that you save overall bandwidth, because originally you would have written out every here the merged result, you would have written out that to memory, so you save overall bandwidth. What you pay is that you need a much more sophisticated algorithm that walks over these binary merges. You have buffers in between. You need to keep track of the fill level of all of these buffers. That causes quite a significant CPU cost, but it saves bandwidth. And since we're bandwidth bound, there's a net saving in the end. Okay.
My other concern with this seems to be more of a blocking. I mean, so when we're waiting on buffers from other NUMA nodes are blocked basically if nobody's taking the buffers. Right? I mean, if you think of this algorithm and try to scale it to multiple threads, how can you ensure that all threads are busy doing something useful without blocking each other?
Well, blocking is probably not the right word. I mean, I agree. While you're doing stuff here, there's yeah, right. But you have that in the when you just do binary merging as well, right? You first do the merging here, and then you do the merging here. And on top of that, I think the problem is not as bad as it might sound. So because you started reading here from that NUMA region and reading from that, and then the hardware is going to see your sequential read and will start prefetching, right? So when you move over here, the hardware is still going to prefetch here, and so yeah.
Once you move there, you move into a remote node. Which
No, the thread always stays on the same.
You're getting data from a remote node.
Yeah, but that doesn't make the difference, right?
This has latency. I mean, well, maybe.
Yeah, but that latency is at least partially hidden by prefetching. Right? You merge in I don't know 1,000 tuples from here and from here, and then you go over here. But the hardware has seen he's just read 1,000 sequential tuples. So let's just prefetch. And then you do the merging here, and by the time you come back, at least parts of that data have already been prefetched, so you don't suffer that full latency. You see what I'm saying?
My point is the local versus remote, right? Accessing local memory versus accessing remote memory. There's usually a 3 to 4x ratio of that. I mean, a thread running a NUMA node 0, if it accesses memory from NUMA node 3, it's going to be 3 or 4 times slower than accessing memory from its local node. That's what I'm saying.
Yeah, I don't see your point really.
So you're assuming that these machines support prefetch of things, so that you can prefetch something and then go off and do something else while you wait for it to get loaded?
At least to some extent, that's what happened. Yeah, of course, it's not. It doesn't magically do everything, right? But
because I'm trying to decide what the difference was between increasing the fan out of a merge versus simply increasing the depth of the buffers.
The thing is when you, basically that, how can I say that? If you just, if you have a low fan out, then you have to repeatedly basically swap out this stuff to memory again and reread it from memory. So that's why you need much more memory bandwidth.
So it doesn't affect the number of remote accesses that you make, right? Because that's going to be the same no matter what. It's the number of local memory accesses that you make that the fan out changes.
Here you're doing basically you're reading all your input data once and writing it out once. If you had done just a binary merge, you would read, write, read this and write, and then again read and write. So you would go twice over all your data, and that costs bandwidth.
I mean, I'm a little bit confused. Where are the buffers?
Well, they end up being in the cache of that thread. So that's why you choose your buffers to have a size that matches your last level cache.
So all those buffers are in node NUMA 0.
Yes, 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 yes.
So the data here is in no way partitioned. So at the end, we will need the one full sorted base run.
Yes, okay.
How do we achieve parallelism there?
Okay, 1 second, okay? I have just one slide that shows the difference that it makes. So in particular, once you scale up to more threads, then what you see here is that at some point you really get no benefit anymore from more threads because you just need so much bandwidth. You completely saturate the memory subsystem. Whereas with this multi-way merging, we keep scaling. The reason why scaling stops here is not the memory bottleneck. It's because here the machine only has 32 physical cores. So over here we start seeing hyperthreads. Okay, so it's a different effect. Yeah. Okay. So now this question about total sorting versus non-total sorting. So there's indeed different strategies. Like, do you want a global sorting at all? What do we do about NUMA? And there's opposing views on that. So one of the views is the one of TU Munich, which is what I'm trying to illustrate here. So what the folks from Munich do is they take their input relation and then do range partitioning. So basically it's hash partitioning, but with an identity hash function, and you look at a certain number of bits, and then do range partitioning, and then so all the low key values end up here, and so on. And then you sort locally in each NUMA region, right? And then you end up with a fully sorted result. Now the claim and here in the range partitioning phase, you do have to cross the NUMA boundaries, right? Whether you do this with merging, as I just sketched before, or whether you do this with range partitioning, that doesn't really make a difference. You do have to cross the NUMA boundary. Huh?
Using local sort and not using hashing, actually we increase our theoretical complexity. So what I was talking about earlier, that instead of this local sorts and partitioning the data, we could just do the entire hashing and have several of buckets ready to be merged.
I didn't quite get that. So, and the strategy of this MPSM, massively parallel sort merge join, is to not sort the other relation, not globally sort the other relation, but just do a local sort. Then you end up with blue, red, green, and yellow data on each of the cores. And then you do the join as follows. On each of the cores, of course, you do the same thing. You do a sequence of joins, merge joins, where you merge this guy with that guy, and then you merge that upper red guy with that red guy, and so on. Okay. So that's one possible way of doing that. We'll see performance numbers in a minute. The one downside of that is you don't end up with a globally sorted result. Because you're merging in values from the same range multiple times, and then those won't be globally sorted. Okay? Alternatively, what you can do is you can do local sorting first, and then do the achieve global sorting with this merging operation, as I sketched before, right? And then you end up with a globally sorted result. This is kind of, you can either choose this or you can do the range partitioning and then the local sorting first. Doesn't make so much of a difference. What we're proposing is to do the same thing for the other relation as well. So create globally sorted data for both tables. And then you can compute the join completely local, so you don't have to do the merging, the merge sort merging across the NUMA boundaries. Okay?
So how much is data skew a problem here? I mean, it's hard. It can be hard to get the partitioning right.
Actually, that's a good point. We haven't really measured a skew problem yet. With this range partitioning, what you're doing is you're building anyway, for partitioning, you need to first build up a histogram of your data, so you know how large your partitions are going to be, because you need to allocate them in memory properly. And then, based on those statistics, you also can choose your partition boundaries properly. If you're doing something like that, you have to do it slightly different. But at least here you have sorted data, so you know something about the data distribution, and then can choose your partition boundaries properly. But that's something indeed where with SKU, that's something that's very high on our priority list. It's true.
So, high-level question. The assumption here is that both tables fit in memory, right?
Yes. So putting things together. Previously I was talking about hash join alone, and there we saw that this radix join has an edge over I call it here naive. It's the hardware oblivious implementation. Here, for a larger data set that we looked at before, this is a data set that was used by the TUM guys. But you get, we saw similar numbers previously also for smaller data sets. Sort merge in comparison to that. What I'm showing here is two sort merge implementations. Basically, it's the two strategies that I had on the slide before. It's the MPSM strategy and the one that uses total global sorting. So this is MPSM and this is global sorting. So our experiments show that global sorting is actually advantageous in the end.
What's the y-axis?
Oh, sorry. Oh, yeah, I forgot to label the y-axis. That's throughput. That's million output tuples per second. Sorry. Oh, yeah, that's a good point. Sorry. Yeah.
So one question. For this type of join, how many rows qualify or all rows qualify?
Yeah, you have, it's like, there's a one-to-one match. Yeah. Okay. So, what you can't see here is that these two implementations don't yet use SIMD acceleration. Introducing SIMD brings quite a bit of an advantage. And what we found makes a real difference is this multi-way merging. So saving bandwidth really in the end helps you quite a bit. And well implemented, what we're seeing in our experiments is that sort merge gets close to hash, but it's not quite as fast as hashing. We previously had the situation that you have to be a little bit careful about the data sets where you reason over. So this is the experiment that I just showed before. If you take a different data set, the picture does change. So this is the data set that we saw before, a gigabyte joined with a gigabyte. Here the well, this is to the advantage of the hash join. One thing that I would like to note when you I've seen several papers and talks about all this topic. I was often surprised how confusing you can present results. So what I'm showing here is how nicely you can fool readers. So for a join, it's really unclear what is really your metric. Do you choose? Do you measure input tuples or output tuples per second? And most of the papers chose to use output tuples per second. The TUM paper chooses, no, actually I did something wrong here, no. No, this is output and this is input on. So this must be output and this must be input, sorry. So depending on what your metric is, you get really different scaling properties. So what's being varied here is that you keep one relation constant and you increase the size of the other relation. So you change the relative size. And if you count output tuples per second, which was the metric on all the slides before and in most of the papers, then you're seeing these characteristics. And if you count input tuples per second, you're seeing this one here. Huh? Of course, input tuples, these are more than output tuples. So that's why you get higher values here. When you sit in a talk and see something saying, someone saying, I have this many 100 million tuples per second, be careful what he's talking about.
Question on the same implementation, did you use AVX? Or
yes. This is actually AVX.
AVX1.
Pardon?
AVX1, I assume, right?
Yeah, AVX2 is not yet available, right? Yeah. So we're actually looking very much forward to try out on Haswell. We don't have hardware yet, but we're very much looking forward. We actually played around a little bit. There was this question before about if sort merge starts to become attractive for joins, what about the other operations such as aggregation? So here is so what I'm comparing here is the state-of-the-art Platt algorithm for which is hash-based for aggregation, and you see the throughput depending on the number of distinct groups for a group by operation. For few groups, hashing gets very cache efficient, but at some point it just gets expensive. Here we see that sort merge is still, depending on the cardinality, it can be significantly slower. But it is very, very robust. I mean, this is something that's I guess known also from classical databases. These are two implementations. One does just a plain sort and then aggregate, and the other one does partial aggregation in between. And when you see in intermediate runs, you have sequences of the same value, you can aggregate them right away.
You can do that with the hash also.
Platt does that to some extent. Yeah. Okay, with that, let me conclude. Basically, I argued about two things. One was about are hardware conscious optimizations worth the effort? This is what I focused on a little bit on the hashing side. And our current results indicate that yes, it is really worth the effort. They're much more robust than you might think, and they're simply faster. We found that hash join is still the faster alternative, but sort merge join is getting close. What is like hard to evaluate numerically is that sort merge has this nice property that it produces sorted output, which might be useful for upstream query processing, right? So that might be another argument for sort merge joins. What we're really looking forward to is have a look at future hardware. Haswell has been announced also with, I think, at least gather support. So in the SIMD registers, you could read from multiple memory locations with one instruction, which of course favors hashing. So we're going to see wider SIMD, which favors sort merge, but we might also see functionality in that direction. And what does that mean to the relative performance? With that, oops. Okay, with that, my app crashed. Sorry. I wanted to say a thank you to in particular, to Chari, the PhD student who did that. Questions? I use up almost all the time. Sorry.
That's right. Thank you very much. Thank you.